Hi, my name is Tyler Turner, and this is my lab number 3 for Physics 2. The purpose of our lab was to predict the behavior of circuits containing resistors in both series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors, all of which using key principles that we've found throughout the course so far and using it in simulation. The two key findings that I will report is that the final resistance was that of 177.6 ohms, and the RC time that I personally recorded averaged to 3.61 seconds. There are a few key principles necessary to understanding and implementing the many questions that were given in the lab. The first is, of course, V equals IR, that of which says the voltage is equal to current multiplied by the resistance of a circuit. And we also had two laws from Kirchhoff's laws. One was for nodes, basically saying that the value of any current that's entering is equal to the value of the exiting current. So those two will always be equal. And if that's not the case, then you know there's something wrong. The second Kirchhoff law was that of pertaining to loops, which was that the sum of all the voltages will ultimately equal 0. We were given a procedure with many different questions, but boils down to three main concepts. The first was for charge conservation and energy conservation in series circuits. We had to perform many of these calculations and basically graph out the different values that we have, which you can see on that graph on the right over that adorable bunny rabbit. The second step was with the RC circuit calculations, in which we had to calculate those and find those values. And the third step was that the time-dependent voltage across the discharging capacitor, in which we had to use simulation from the tools we were given in order to answer those questions. There were a few assumptions that we had to make in the lab. Most of them were that simply that this is a simulated environment that we were using, so obviously this won't match the real world values in any such application because the code assumes that it is a perfect world and that there won't be like any errors and things like that. So that's one key assumption that we have to recognize during this lab. There are a few possible sources of error that we can see through the lab. One could be like minor rounding and calculation errors of the simulation, because again, it can't be completely perfect. Another could be the timing precision, because we had to time on our own stopwatches or cell phones, and so there could have been some small errors with that, which could have shifted the results. And lastly, there are the limits of graphing estimations, as you can see on the slide before. Let me go back to that real quick. You can see sort of the trends are a little iffy, like long term, as there are more ohms. Like, would this necessarily show the right trend? It's kind of impossible to say that with such limited data. So that's another source of error, that these trends might be different in real life. We were also given two key hypothetical questions. So the first is basically saying, what if we were to do this experiment in real life and use an actual ammeter instead of an ideal simulated one, and what's different about them and how would it have affected the circuits that we hooked it up to? So basically, if we did this in real life, there would definitely be more resistance because, again, ammeters aren't perfect. They don't match this perfect simulated environment that we're using. So again, one of our key formulas, V equals IR, we know that if there is more resistance, then this is actually going to decrease our current and basically make if our goal of the system is to have more current, this is going to not really accomplish the goal as well, because this is going to decrease our current. So ultimately, answering this question shows us that in real life, there's going to be more resistance, less current than maybe the most optimal values that we're seeking to make our circuit work really well. The second hypothetical question we're giving is saying, what if we were to do this experiment in real life using like a real battery, a real capacitor with no resistor in the circuit, and how quickly would our ideal model predict the capacitor to reach full charge, and would this prediction happen in real life? So essentially, if we were to try to find these values with the simulator, it would be instant because, again, it's a simplified simulation model. So a real life replication would probably take a short amount of time before achieving this current, because, again, instantaneously, that would obviously be a goal maybe when you're designing one of these, but in the real world, it's going to take maybe a few milliseconds or maybe 1 second. We don't know the exact time, but we know it would not just happen, out of nowhere. So that's answering those two questions. And with that, that is the end of the lab. Thank you for watching. Have a nice day.